All right, this is Mr. Gillum, and today we're going to learn a little more about proportional relationships. Some of our terminology today is going to change, and nothing actually changes about what we're talking about as far as proportionality goes, but some of the vocabulary is just a little different. So instead of seeing the letter X, you're going to see the word input. Okay, X is traditionally used as an input value. Output will be referring to the Y value. The X value we also consider the independent variable. A lot of times our unit of time is our independent variable. Okay. Our output, or the Y value, we consider to be the dependent variable. Okay, is the dependent variable. And that's just a variety of different things depending on what the X value is. All right, so today, when you see inputs, you should be thinking the X values. When you see outputs, you should be thinking of the Y values. We call the X values independent. Time is one that's very commonly used as an independent variable. And we use the Y values, we call them the dependent values. One of the things that we talked about in being a proportional relationship is that it must be linear. But we also saw some graphs of lines that were linear, but were not proportional. All right, this will be proportional. It meets all the requirements of being both linear and going through the origin 0, 0. This graph, the second graph, would be non-proportional. It is linear though. However, it does not cross through the point 0, 0. And so we talked about this yesterday, and we identified different types of proportional and non-proportional graphs. And today what we're going to do is we're actually going to look at the T-chart. Okay. We also decided that in a T-chart sometimes we could have 2, 4, 6, 12, 8, 16, whatever they were, and we would see that the ratio of y to x, if it is the same, 4 over 2, 12 over 6, 16 over 8, if it's the same, then it would be proportional. Yes, proportional. But we also saw T-charts that had the same, like had a pattern in them. 1, 2, 3, 4, 5, and 2, 3, 4, 5, 6 that were not proportional because 2 over 1 and 3 over 2 and 4 over 3 are not the same ratio. So although there's a pattern, it doesn't make it proportional. However, because each of these columns follows a pattern, the same pattern, they are considered linear. They are linear, but they're not proportional. Okay, and so today when I say linear, we need to see what the pattern is, and we need to decide what the missing value is that also follows the pattern. So we would like these to all be linear. So they all need to follow the same pattern. Then we can determine whether or not the relationship is proportional. So let's take a look at the inputs and outputs. And I know the numbers are kind of big, but let's see if there's a relationship between 53 and 73. Or sorry, 55 and 73, 65 and 83, 90 and 108, 20 and something, 38 and 56. Now, Mr. Gillum's pretty good at finding patterns in numbers, and Dr. Kaboom even said, hey, math, it's all about patterns. Now, they don't put the numbers in order for us this time, which is a little frustrating. The inputs kind of jump around 55, 65, 90, 20, 38, and really those inputs are X values and the outputs are Y values. And the outputs are kind of jumping around, but there is a relationship between the inputs and outputs. If we add 18 to each one of these, I see that it will be the Y value. And so what I'm going to do is I'm going to say for this to be linear, 20 will also have to be added with 18 to find the value of 38. And so what I'm going to do is I'm going to just start by looking at some of the ratios, and I'm going to pick the smaller numbers first. And so I see 20 and 38 are the smallest two numbers, so let's look at those ratios first. The Y to X ratio, this is going to help us to tell whether or not the relationship is proportional. So I'm going to compare 38 to 20 and 56 to 38 first. And of course, if these don't match, then I know right away it's not proportional. If they do match, I'll keep going to compare all the numbers. So let's just see here. If I reduce 38 20ths, I see that they're both even numbers. I would have 19 tenths. And again, 56 and 38 are both even numbers, so let's reduce those by a factor of 2 as well. 28 19ths. Now, unfortunately, 19 is what we call a prime number. There are no factors of 19 besides 19 and 1. And so this fraction is in its lowest reduced form, and this fraction is in its lowest reduced form. And so you can see that this is not proportional because these are not equal. Okay, they're not equal. So, unfortunately, this would be non-proportional. Okay, non-proportional. It is linear because we made sure to follow the same pattern, but it is not proportional because the ratios of y to x do not match. So let's take a look at this next example, and I'm looking at 24 and 21 and their relationship. 18 and 15, 46, 43, 36, 33, and this one might be a little more obvious than the last one. It looks to me like I am subtracting 3 from each of these values. And so to keep this relationship linear, what makes the table linear, I'm going to subtract 3 from 95. I'm going to say it's 92. And so now it is a linear relationship that every single input has the same pattern mapping to the output. Let's see if the ratios are the same when we compare y to x. 21 over 24, that one won't be too bad to reduce. And let's do 33 over 36. And we're just going to start with 2 because right away if one of them doesn't match, I'm going to know for sure that it is not proportional. So let's see here. We're going to find out if these are equal. Let's put them in both reduced form. I know 3 goes into 21 and 24, 7 and 8 times. I know 3 goes into 33 and 36, 11 and 12 times. And as you can see, these are the lowest forms of these fractions, and they are not the same. So I know that these fractions are not, that means the ratio is not equal, and therefore this is non-proportional. Okay, so even though it is linear, it is non-proportional. Let's take a look at this next one here. And I'm mapping 4 to 16, 5 to 20, 8 to 32, something to 24, 7 to 28. And the pattern I notice is that they're being multiplied by 4 each time. Each input is being multiplied by 4. So something times 4 equals 24, or I could think of it backwards and say 16 divided by 4 is 4, 20 divided by 4 is 5, 32 divided by 4 is 8, 24 divided by 4 would be 6. And so now I have a linear relationship, just filling in the pattern. Is it proportional? Let's find out. If I divide the y compared to the x, 16 over 4, 20 over 5, 32 over 8, 24 over 6, and 28 over 7, do all of those ratios match? Well, 16 divided by 4 is 4, 20 divided by 5 is 4, 32 divided by 8 is 4, 24 divided by 6 is 4, and 28 divided by 7 is 4 as well. So as you can see, because the ratio matches in every instance, this is proportional. It is linear and proportional. Meaning that if I were to draw this graph, it would go through the origin if I mapped the graph onto a coordinate plane. Okay? And so I put 4 more examples on there, but I think you kind of get the idea. Right now we're looking for the pattern to make the inputs and outputs stay the same, that relationship. And then we need to decide by comparing the ratios if the relationship is proportional or not. So I'm going to go ahead and go right over these, but if you'd like to try them, again, one thing I will mention is that that's representing inputs, those are the x values, and outputs are the y values. So just keep in mind when you're comparing your ratios, you're comparing 63 to 7 and 72 to 8 in that order, okay? The inputs and the outputs. You might want to write yourself a note there. Just because the chart is sideways, x on the top, y on the bottom, x is the inputs, y is the outputs. But we're not going to go ahead, we're not going to take any more time to go over these charts because there's one more thing I want to learn about today in this video. And in this case, it says create a table. It says for every shirt made, 2 buttons are used. Create a table showing the buttons needed, making up to 5 shirts. Then plot the values on the coordinate plane. So let's talk about the shirts and the buttons. And I'm going to say this is the input, or the X value, and this is the output, or the Y value. And the reason I'm going to say that shirts are our input is because the number of buttons depends on how many shirts we need. Okay, so this is dependent on how many shirts we need, which we call the independent variable. And so that's why I'm labeling the input as shirts and the output as buttons, because the number of buttons depends on how many shirts there are. The number of shirts does not depend on how many buttons, but the buttons does depend on how many shirts. And so there's a relationship here. It says for every shirt made, 2 buttons are used. So if we had 1 shirt, we would need 2 buttons. And if we had 2 shirts, we would need 4 buttons. 3 shirts, 6. 4 shirts, 8. 5 shirts, 10. Okay? Each shirt adds 2 buttons. So let's just take a look here. If I were to graph this relationship, it's going to show me what type of relationship I have. So let's go ahead and graph x comma y. So I have the coordinates 1 comma 2, 2 comma 4, 3 comma 6, 4 comma 8. These are my input and output values, and 5 comma 10. Okay, those are my coordinates that I'm going to graph. So I'm going to start, and this is 0, 0 here. And so I'm going to go over 1 up 2. I'm going to go over 2 up 4. I'm going to go over 3 up 6. My markers are a little pudgy for this. Over 4 up 8. And over 5 up 10. All right. And if I were to graph this, and if this is a perfect line, you would see that it goes through. I'm going to make a big fat dot there. It would go through 0, 0. And so I would say that this relationship is proportional. Okay, so yes, this relationship would be proportional. It also goes to show if I compare 2 to 1, or 4 to 2, or 6 to 3, or 8 to 4, or 10 to 5, that these ratios are all equal to 2. And so that also shows that this is a proportional relationship. It doesn't say whether or not it's proportional, but we know through these 2 facts that it must be proportional. It is linear, it goes through the origin, and the ratio of y to x is the same. In this case, it says every minute 4 books are printed. Create a table showing the books printed over the course of 5 minutes, then plot the values in the coordinate plane. In this case, it says every minute 4 books are printed. So I'm going to call this minutes on the top, the input, and the books printed on the bottom, the output. So input and output. We know that would be x and that's y. And we know that the y is the dependent value. I'm going to tell you why I'm going to make the books y here in just a second, and the x is the independent value. The number of books that we can make depends on how long we're printing them. And so the books is dependent on the minutes. And we talked about earlier too, in our independent variable, it's almost always, if you see a time, it is always the independent variable. And so this would be an instance where, depending on how long we are printing books, is going to change how many books we can actually get printed. In this case, it says every minute 4 books are printed. So after 1 minute, there are 4 books. 2, there would be 8, 3, 12, 4, 16, 5, and 20. And so again, I could graph this and see the relationship. And because I only need 5, I'm going to go ahead and say that this is 1, 2, 3, 4, and 5, because it's really hard for me to graph accurately with the squares being so small. So I'm going to go ahead and do it this way. So I'm going to call this some minutes, and this guy books, and take a look at the graph here. So over 1 up 2, there's a spot. Over 2 up 8. Oop, we're going to go off the map now, so I guess that was a bad plan. Maybe we shouldn't do that. We'll go over 1 up 4 right there, over 2 up 8 right there, over 3 up 12 there, over 4 up 16, and over 5 up 20. And so we got a skinnier, taller line, but if I was able to draw a perfect line through those points, you would notice that it goes through the origin. And you would also notice that the ratios, 4 to 1, 8 to 2, and so on, are all the ratio of 4. So this would also be proportional relationship. The important part is going to be identifying which is the independent and which is the dependent variable. In this case, the number of books depends on how long